Hello there and welcome to the Sleepy at Night channel. Tonight we will be exploring one of the most profound mysteries of existence. Time itself. That unseen river that carries us onward, that shapes every moment of our lives yet remains so hard to grasp. We think we understand what time is until we try to describe it. We feel its passage in every heartbeat, every sunrise, every memory that slowly fades. But time is not what it appears to be. It bends, it stretches, it flows at different speeds depending on where you are and how fast you move. Tonight we will journey through the nature of time, through the insights of relativity, and through the strange and beautiful ways the universe keeps its clock. If you enjoy these quiet explorations, I invite you to like and subscribe or share a simple thought down in the comments. It helps others find their way here, to one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the gentle flow of time itself to carry you into sleep. Let's begin. Time feels like it flows at a steady pace. But this is an illusion. We experience time as a constant companion, ticking forward at the same rate, whether we are awake or asleep, young or old. Each second seems to follow the last with perfect regularity. Our clocks measure it precisely, dividing each day into 24 hours, each hour into 60 minutes, each minute into 60 seconds. This regularity reassures us. It gives structure to our lives. But beneath this familiar rhythm lies a deeper truth. Time does not flow the same way for everyone. It is not a universal river carrying all things equally. Instead, time is flexible, malleable, shaped by gravity and motion in ways that challenge our everyday intuition. Einstein showed us that time is relative, not absolute. For centuries, people believed time was the same everywhere, that a second on Earth was identical to a second on the Moon, on Mars, or in the furthest reaches of space. Then came Albert Einstein. In 195, he published his special theory of relativity, forever changing how we understand time. He revealed that time is not separate from space, but woven together into a four-dimensional fabric called spacetime. In this framework, time becomes relative. It depends on how fast you are moving and where you are in a gravitational field. Two observers moving at different speeds will measure time differently. What seems like 1 hour to a traveler moving near the speed of light might be years to someone standing still. This was not merely theoretical speculation. It was a prediction based on the fundamental nature of light and motion, and every experiment since has confirmed it. Time is not the steady universal clock we once imagined. It is something far stranger and more wonderful. The speed of light is the universe's absolute speed limit. At the heart of relativity lies one unchanging constant, the speed of light. In a vacuum, light travels at exactly 299,792,458 meters s. This speed is not just fast. It is the ultimate speed limit of the universe. Nothing with mass can reach it. Nothing can exceed it. No matter how powerful your engine or how much energy you expend, you will always find light racing ahead at the same speed. What makes this truly remarkable is that the speed of light is the same for everyone regardless of how fast they are moving. If you are standing still and measure a beam of light, you will find it travels at this speed. If you are racing forward at 90% the speed of light and measure that same beam, you will still find it travels at the same speed relative to you. This constancy seemed impossible when Einstein first proposed it. But it is the key to understanding relativity because the speed of light never changes. Everything else must. Time and space themselves adjust to preserve this universal constant. Light from the sun takes 8 minutes to reach Earth. The light that warms your face on a sunny day did not just leave the Sunday. It began its journey 8 minutes and 20 seconds ago. During that time, it crossed the vast gulf of space between our star and our planet, traveling through the cold vacuum at the speed of light. This means that when you look at the sun, you are not seeing it as it is now. You are seeing it as it was 8 minutes in the past. If the sun were to suddenly vanish, we would not know for 8 minutes. The light already on its way would continue to arrive and the sky would remain bright. This delay reminds us that looking at anything means looking into the past. The farther away something is, the older the image we receive. The moon's light is 1 second old when it reaches us. The nearest star beyond the sun, Proxima Centauri, shows us its light from over 4 years ago. And the most distant galaxies we observe reveal themselves as they were billions of years in the past. Every glance across distance is a glance across time. Time slows down as you approach the speed of light. Imagine boarding a spacecraft capable of traveling at 99% the speed of light. You accelerate away from Earth, racing through the solar system and beyond. To you inside the ship, time seems perfectly normal. Your watch ticks steadily. You breathe, you think, you move just as you always have. But to observers on Earth watching you go, something strange happens. Your clock appears to slow down. The faster you travel, the more pronounced the effect becomes. This phenomenon is called time dilation. And it is not an illusion or a trick of perception. It is real. If you spent 1 year traveling at such speeds and then returned to Earth, you would find that many years had passed here. Your friends and family would have aged far more than you. You would have journeyed into their future simply by moving very fast. This is not science fiction. It is a consequence of the universe's structure. Time itself runs slower when you move faster. And the closer you get to the speed of light, the more dramatic the effect becomes. At the speed of light, time stops entirely for the traveler. If somehow you could reach the speed of light, something even stranger would occur. From your perspective, time would stop completely. The journey from one end of the galaxy to the other would seem instantaneous. You would experience no passage of time at all. To the outside world, the journey would still take thousands or millions of years. But for you, it would be a single moment with no duration. This is why light itself experiences no time. A photon emitted from a distant star billions of years ago does not age during its journey. From the photon's perspective, its creation and its absorption into your eye are the same instant. The entire history of the universe happens in zero time from light's point of view. Of course, nothing with mass can actually reach the speed of light. It would require infinite energy. But this thought experiment reveals something profound. Time is not a universal experience. It depends entirely on your motion and position in the cosmos. Astronauts age slightly slower than people on Earth, even at speeds far less than the speed of light. Time dilation occurs. Astronauts aboard the International Space Station orbit Earth at about 28,000 km/h. This is fast by human standards, but still only a tiny fraction of light speed. Yet, even at this modest velocity, time dilation is measurable. Astronauts aboard the station age slightly slower than people on the ground. The difference is small, only a few milliseconds over months in orbit, but it is real and measurable with precise atomic clocks. This effect has been confirmed countless times. Atomic clocks flown on airplanes run slightly slower than identical clocks left on the ground. Satellites in orbit must account for time dilation in their programming, or GPS systems would quickly become inaccurate. Every high-speed journey, no matter how brief, involves a tiny shift in the passage of time. We do not notice it in our daily lives because the speeds we travel are so slow compared to light. But the effect is always there, woven into the fabric of motion itself. Time also slows down in strong gravitational fields. Speed is not the only thing that affects time. Gravity does too. Einstein's general theory of relativity, published in 1915, revealed that massive objects warp the fabric of space-time around them. This warping is what we experience as gravity. But it also affects time. The stronger the gravitational field, the slower time passes. If you stand at the bottom of a deep valley and a friend stands on a nearby mountain peak, time flows slightly faster for your friend than for you. The difference is minuscule, but it is real. Near extremely massive objects, the effect becomes dramatic. Close to a black hole where gravity is immense, time slows so profoundly that clocks almost stop. An observer far away would see you moving in extreme slow motion as you approached the black hole's edge. This is not because of any mechanical failure. Time itself is running slower for you in that intense gravitational field. Every second you experience might correspond to hours, days, or even years passing elsewhere in the universe. Clocks on mountain tops run faster than clocks at sea level. You do not need exotic locations to observe gravitational time dilation. It happens right here on Earth. Atomic clocks placed on mountain tops tick slightly faster than identical clocks at sea level. The difference is tiny, measured in billionths of a second, but modern instruments can detect it easily. The reason is simple. The mountain top is farther from Earth's center of mass. So the gravitational field is slightly weaker there. Weaker gravity means time flows faster. This effect has practical consequences. The GPS satellites orbiting high above Earth experience both time dilation from their speed and time speeding up from weaker gravity. Engineers must account for both effects, or the system would accumulate errors of several kilometers per day. The fact that your phone can pinpoint your location to within meters is proof that relativity is not just abstract theory. It is woven into the technology we use every day. Time does not pass uniformly across Earth's surface. It varies with altitude, with motion, with the subtle differences in gravitational pull from mountains, valleys, and the mass distribution beneath our feet. GPS satellites must correct for relativity to stay accurate. Every GPS satellite carries an atomic clock that sends time signals to receivers on the ground. These signals allow your phone or navigation device to calculate your exact position. But here is the remarkable part. If the satellites did not correct for relativistic effects, the entire system would fail within minutes. The clocks aboard the satellites run faster than clocks on Earth because of weaker gravity, but slower because of their orbital speed. The combined result is that satellite clocks gain about 38 microseconds per day compared to ground clocks. Engineers program the satellites to tick at a slightly altered rate to compensate for this. Without this adjustment, GPS positions would drift by about 10 km per day, making the system useless. Every time you check your location, you rely on equations first written by Einstein more than a century ago. Relativity is not merely a curiosity for physicists. It is a vital part of modern life, quietly enabling technologies we depend on every day. Gravity bends spacetime like a heavy ball on a stretched sheet. To understand how gravity affects time, it helps to picture spacetime itself. Imagine spacetime as a flexible fabric, like a stretched rubber sheet. Now place a heavy ball representing a massive object like Earth or the Sun onto this sheet. The ball creates a depression, a curve in the fabric around it. This curvature is gravity. Objects moving nearby naturally follow the curves of this warped spacetime, which is why planets orbit stars and moons orbit planets. But this warping also affects time. The deeper you are in the gravitational well, the more spacetime is curved and the slower time flows. Imagine two clocks, one resting on the surface of a massive planet and one floating far away in empty space. The clock on the planet sits deep in the curved region of spacetime, while the distant clock rests on flatter, less curved spacetime. Time runs slower for the clock in the deeper gravitational well. This is not because the clock is faulty. It is because time itself moves at different rates depending on the curvature of spacetime around you. Massive objects warp the space around them. And this warping is gravity. When Einstein proposed that gravity was not a force pulling objects together, but instead a curvature of spacetime itself, it seemed almost mystical. Yet experiments have confirmed it again and again. Massive objects like stars and planets do not pull on other objects. Instead, they curve the spacetime around them, and objects simply follow the straightest possible paths through that curved space. This is why Earth orbits the Sun. It is moving in a straight line through curved spacetime. The more massive the object, the greater the curvature. A small asteroid barely disturbs spacetime. A star like the Sun creates a noticeable curve. A black hole warps spacetime so severely that nothing, not even light, can escape from within a certain boundary. This curvature is not just a geometric curiosity. It is the essence of gravity. And because spacetime includes time, the curvature also affects how time flows. Gravity and time are inseparably linked, two aspects of the same underlying reality. Light bends when passing near massive objects, proving spacetime curves. One of the most dramatic confirmations of general relativity came in 1919, just a few years after Einstein published his theory. During a total solar eclipse, astronomers measured the positions of stars near the Sun's edge. According to Einstein, the Sun's mass should curve spacetime, bending the path of starlight passing nearby. The stars should appear slightly shifted from their true positions. The measurements confirmed this. Starlight was indeed bent by the Sun's gravity, exactly as Einstein predicted. This observation made headlines worldwide and turned Einstein into a celebrity. It was direct evidence that spacetime could be warped by mass. Since then, astronomers have observed this effect countless times. Massive galaxy clusters bend light from more distant galaxies, creating arcs and multiple images. This phenomenon, known as gravitational lensing, allows scientists to map the distribution of dark matter and study objects otherwise too faint to see. Every bent beam of light is a signature of curved spacetime, a visible trace of gravity's influence on the fabric of reality. Black holes stretch time to its extreme limits. Of all the objects in the universe, black holes represent the most extreme warping of spacetime. They form when massive stars collapse at the end of their lives, compressing their entire mass into an infinitely small point. The gravity near a black hole is so intense that it creates a boundary called the event horizon. Once anything crosses this boundary, it can never escape. Even light traveling at the universe's maximum speed cannot break free. Near the event horizon, time dilation becomes extreme. If you were to hover just outside a black hole and watch a friend fall in, you would see them slow down as they approached the horizon. Their movements would become sluggish. Their clock would tick more and more slowly. Eventually, they would appear frozen in time, never quite crossing the boundary. Meanwhile, from your friend's perspective, they would pass through the event horizon in a finite amount of time, experiencing nothing unusual at that moment. The difference arises from the extreme curvature of spacetime. Time near a black hole runs so slowly compared to time far away that the two perspectives become radically different. Falling into a black hole, you would see the universe age rapidly. Imagine you are in a spacecraft approaching a black hole. As you draw closer, you begin to feel the effects of extreme spacetime curvature. If you looked back at the universe behind you, something astonishing would occur. You would see time speed up. Stars would race through their life cycles. Galaxies would spin faster. And the cosmos itself would age before your eyes. Events that would normally take millions or billions of years would unfold in what seems like moments to you. This is the other side of time dilation. While you experience time normally, the outside universe appears to fast forward. The closer you get to the event horizon, the stronger the effect becomes. By the time you cross the horizon, assuming you could survive, the entire future of the universe outside would have passed in an instant from your perspective. Of course, once inside, you would be doomed to fall toward the singularity at the center, where the laws of physics as we know them break down. But in those final moments, you would have witnessed the universe's distant future. All because of the way gravity votes time. At the event horizon, time appears to stop for outside observers. The event horizon is the point of no return around a black hole. For someone watching from a safe distance, an object falling toward a black hole would seem to slow down as it neared the horizon. Its image would become increasingly redshifted, the light stretched to longer wavelengths as it climbs out of the deep gravitational well. Eventually, the object would appear frozen, suspended at the edge of the horizon, never quite falling in. This is because, from the outside perspective, time at the event horizon has slowed to nearly zero. But for the falling object, time continues normally. The traveler would cross the event horizon in a finite amount of their own time, experiencing no special sensation at the moment of crossing. This divergence in perspectives is one of the strangest consequences of relativity. There is no single objective answer to the question of whether the object has crossed the horizon yet. It depends on who is asking. For outside observers, the crossing takes infinite time. For the traveler, it happens in moments. Both viewpoints are equally valid. Time is not a single universal stream, but a tapestry of different flows, each shaped by motion and gravity. Gravitational time dilation has been measured with atomic clocks. The effects of gravitational time dilation are not just theoretical. They have been measured directly in laboratories. Here on Earth, in 2010, scientists at the National Institute of Standards and Technology used ultra-precise atomic clocks to measure time dilation over a height difference of just 33 centimeters, about 1 foot. They found that the higher clock ran faster than the lower one, exactly as Einstein predicted. This experiment showed that you do not need extreme environments like black holes to observe relativistic effects. Even the gentle gravity of Earth produces measurable differences in time over distances you could step across in a single stride. Since then, portable atomic clocks have become even more precise, allowing scientists to measure gravitational time dilation in elevators, on city streets, and across landscapes. These experiments are not only tests of relativity. They are opening new possibilities for using time itself as a tool to measure gravity, map Earth's shape, and probe the structure of spacetime with unprecedented accuracy. Every massive object, from a planet to a star, votes time around it. Wherever there is mass, there is curvature of spacetime. And wherever spacetime curves, time flows differently. This is not limited to exotic objects like black holes. Every planet, every star, every massive object in the universe creates its own gravitational well and slows time nearby. The effect is stronger near more massive and compact objects, but it is always present. When you stand on Earth, time flows slightly slower for you than for someone floating in the empty space between galaxies. When you visit another planet, time would flow at a different rate depending on that planet's mass and size. If humans ever establish colonies on other worlds, settlers on a dense planet with strong gravity would age slightly slower than those on a less massive world. Over generations, this could lead to measurable differences in biological aging. Time is not merely a backdrop to the universe. It is shaped by the universe, woven into its very structure. Time and space are not separate, but interwoven into spacetime. Before Einstein, people thought of space and time as separate entities. Space was the stage on which events unfolded, and time was the universal clock ticking steadily for everyone. But relativity revealed a deeper truth. Space and time are not independent. They are aspects of a single four-dimensional fabric called spacetime. Events do not happen in space at a certain time. They happen at specific points in spacetime. This union means that measurements of space and time are intertwined. If you move through space, you also move through time in a way that depends on your speed and the gravitational fields you pass through. There is no universal present moment stretching across the cosmos. Instead, simultaneity itself is relative. Two events that appear simultaneous to one observer may occur at different times for another observer moving at a different speed. Spacetime is the true arena of reality. And our everyday experience of separate space and time is simply a limited perspective, valid only at slow speeds and weak gravity. Moving through space means moving through time as well. When you walk across a room, you are not only moving through space. You are also moving through time. In fact, everything in the universe is always moving through spacetime at the speed of light. This seems strange because we do not usually move through space at light speed. The key is that motion through spacetime includes both space and time. When you are sitting still, you are moving through time at the maximum rate. When you begin moving through space, some of your motion through time is converted into motion through space. The faster you move through space, the slower you move through time. This is why time dilation occurs. Your total speed through spacetime remains constant, but the balance between spatial motion and temporal motion shifts. At the speed of light, all of your motion is through space and none is through time. This is why photons do not experience time. Understanding this helps make sense of relativity's strange predictions. You are always moving at the same total speed through spacetime. It is simply a matter of how that motion is divided between space and time. The twin paradox shows how motion affects aging. One of the most famous thought experiments in relativity is the twin paradox. Imagine two identical twins. One stays on Earth while the other boards a spacecraft and travels at high speed to a distant star and back. When the traveling twin returns, they discover they have aged less than their sibling who stayed behind. This is not just theoretical. It is a real consequence of time dilation. From the traveling twins' perspective, time flowed normally aboard the spacecraft. But because they were moving at high speed, time passed more slowly for them relative to Earth. From Earth's perspective, the traveling twins' clock ran slow during the journey. Both perspectives are consistent. The traveling twin truly experiences less time passing. This means that high-speed space travel is a one-way ticket to the future. You can move forward in time by traveling fast, but you can never go back. The stay-at-home twin ages more, and there is no way to reverse the effect. If one twin travels near light speed, they return younger than their sibling. Let's make the twin paradox more concrete. Suppose the traveling twin journeys at 99.5% the speed of light to a star 20 light-years away and then returns. The round trip, as measured by Earth clocks, takes about 40 years. But for the traveling twin, time dilation means the journey feels much shorter. Due to the effects of relativity, the traveling twin might experience only 4 years passing during the entire trip. When they return to Earth, 40 years have passed here, but the traveler has aged only 4 years. They are now 36 years younger than their twin who stayed home. This is not an illusion or a trick. It is the direct result of moving at high speed. The traveling twin has taken a shortcut through time, moving into the Earth twin's future. This consequence of relativity has been confirmed indirectly through experiments with particles that decay at high speeds. Particles called muons, created in Earth's upper atmosphere, should decay before reaching the ground. But because they travel at speeds close to light, time dilation allows them to survive the journey. They experience less time, just like the traveling twin. This is not a paradox, but a proven feature of relativity. The twin paradox is not truly a paradox at all. It only appears contradictory if you assume time flows the same for everyone. Once you accept that time is relative, the outcome becomes clear. The traveling twin undergoes acceleration and deceleration, changing reference frames, while the Earth-bound twin does not. This asymmetry is crucial. It is not only about relative motion. It is about the path each twin takes through spacetime. The traveling twin's path through spacetime is shorter in terms of time, even though it is longer in terms of space. Spacetime geometry determines how much time each twin experiences, and the result is unambiguous. The traveling twin ages less. This has been verified with real experiments using atomic clocks on airplanes and satellites. In every case, The moving clock shows less elapsed time when reunited with its stationary counterpart. The universe obeys the laws of relativity with flawless consistency. Muons demonstrate time dilation in every particle physics experiment. Muons are subatomic particles similar to electrons but roughly 200 times heavier. They are unstable and decay quickly, with a half-life of only 2.2 microseconds. This means that in their own reference frame, half of any collection of muons will decay within about 2 microseconds. When cosmic rays strike Earth's atmosphere high above the surface, they produce showers of muons that rain down toward the ground. Here is the puzzle. Even traveling at nearly the speed of light, muons created 15 kilometers up should decay long before reaching sea level. The trip takes far longer than their brief lifetimes. Yet we detect muons at ground level in large numbers. The explanation is time dilation. From Earth's perspective, the muons clocks run slow because they are moving so fast. What is 2 microseconds in their own frame becomes much longer in hours, giving them enough time to reach the ground. From the muons' perspective, they still experience only 2 microseconds, but the distance they must travel is shortened due to length contraction, another relativistic effect. Both viewpoints agree. The muons reach the surface, proving that time dilation is not merely theory but observed reality. Traveling to distant stars would allow you to journey into Earth's future. Imagine a mission to a star 100 light-years away. A spacecraft traveling at 99.99% the speed of light could complete the journey in just over 100 years as measured from Earth. But for the astronauts aboard, time dilation would dramatically compress the trip. Due to relativity, the crew might experience only about 1.4 years passing during the journey. When they arrive at the distant star, they would have aged very little, while more than a century has passed on Earth. If they chose to return, the same effect would occur on the way back. By the time they reached home, over 200 years would have passed on Earth, while the crew would have aged less than 3 years. They would step out of their ship into a transformed world, meeting the descendants of people they once knew. This is not science fiction. It is the logical outcome of relativity. High-speed space travel is travel into the future. The faster you go, the farther ahead you leap. Interstellar travel becomes a one-way trip into the future of those left behind. This creates a profound implication for future space exploration. Any civilization that develops near light-speed travel must confront the reality that their explorers will become time travelers. Those who leave will return to find their world changed beyond recognition. Friends, family, entire cultures may be gone or transformed. The mission is not only a journey across space, but across time as well. This is not symmetrical. The travelers can move into the future of those left behind, but they can never return to the past. There is no way to reverse time dilation. The journey is one-directional through time. For this reason, interstellar voyages at relativistic speeds would require not only technological ability, but also deep psychological and cultural preparation. Crews would be saying goodbye not just to a place, but to an era. Their return, if it happens, would be to a future they can only imagine. Time does not have a single universal present moment. One of the most startling revelations of relativity is that there is no single universal now. Events that appear simultaneous to one observer may occur at different times for another observer moving at a different speed. Imagine two people, one on Earth and one on a spaceship traveling away at high speed. They synchronize their clocks when the ship departs. Later, the person on Earth believes it is noon. They might assume it is also noon on the distant spaceship. But according to relativity, there is no objective answer to whether it is noon on the ship. Depending on the ship's speed and direction, the present moment on the ship could align with the past, the present, or even the future of Earth time. Simultaneity is relative. Different observers slice spacetime into moments in different ways. There is no universal present stretching across the cosmos. Instead, the universe contains countless overlapping perspectives, each equally valid. Time is deeply personal, shaped by your path through spacetime. Different observers can disagree on the order of events. If two events are separated by enough distance in spacetime and occur close enough together in time, observers moving differently can even disagree about which happened first. Imagine two distant supernovae exploding. To one observer, supernova A might occur before supernova B. To another observer moving at a different speed, supernova B might occur before supernova A. Both observations are correct within their own frames of reference. This does not create paradoxes because the events cannot influence one another. If supernova A could send a signal to affect supernova B, then all observers would agree on the order. The speed of light ensures that causally connected events preserve their sequence for everyone. But for events too distant to affect each other, their ordering becomes relative. This challenges our intuitive sense of a single timeline with a fixed sequence. Instead, spacetime is structured so that causality is preserved, while the order of unrelated events can vary depending on perspective. Relativity forbids faster-than-light travel to prevent paradoxes. The speed of light is not merely a speed limit. It is a fundamental barrier woven into the structure of causality. If you could travel faster than light, you could move backward in time relative to some observers. This would create causality paradoxes, situations where effects precede causes or where you could interact with your own past. Consider this. If you sent a faster-than-light signal to a distant location, and someone there sent a faster-than-light signal back, the return signal could arrive before the original was sent. You could receive a reply before asking the question. This violates the principle of causality, the idea that causes must come before effects. The universe does not allow this. By establishing the speed of light as an absolute limit, relativity ensures causality is preserved. No matter how much energy you use, you cannot accelerate beyond light speed. The equations of relativity show that doing so would require infinite energy. The speed of light is the ultimate cosmic limit, safeguarding the logical structure of time itself. Nothing with mass can reach the speed of light. As an object with mass accelerates closer and closer to light speed, something remarkable occurs. It becomes increasingly difficult to accelerate further, as the object's inertia increases, requiring more and more energy for smaller and smaller gains in speed. At 90% the speed of light, the object already has significantly more inertia than at rest. At 99%, the increase is dramatic. At 99.9%, even more so. As you approach light speed, the energy required to accelerate further grows without limit. Reaching the speed of light would require infinite energy, which is impossible. This is not a technological limitation. It is a fundamental property of spacetime. Particles with mass can get arbitrarily close to light speed, but they can never quite reach it. Only massless particles like photons can travel at light speed, and they have no alternative. They must always move at that speed. For them, there is no slowing down or speeding up. Light always travels at the speed of light. Light moves through spacetime along special paths called null geodesics. In the geometry of spacetime, paths fall into three categories. Timelike paths are followed by objects moving slower than light. Spacelike paths connect events that cannot influence each other because they are too far apart in space and too close in time. And then there are null geodesics, the paths followed by light. These paths are unique because they represent zero spacetime interval. The spacetime distance along a light ray is zero. This mathematical feature reflects the fact that photons experience no time. From a photon's perspective, its entire journey, no matter how long it appears to us, occurs in a single instant. Light rays define the boundary between past and future. Your light cone, the set of all possible light paths passing through you, divides spacetime into events that can affect you, events you can affect, and events that are causally disconnected from you. Understanding these paths helps explain how information and influence propagate through the universe, always constrained by the speed of light. Photons experience no time at all during their journeys. Imagine being a photon, though of course you cannot. If you could ride along with a beam of light, the universe would appear frozen. No time would pass between the moment of your creation and the moment of your absorption. A photon emitted from a star 10 billion light-years away experiences its entire journey to your eye as a single timeless instant. From the photon's perspective, the universe has no duration. This is the extreme limit of time dilation. At light speed, time stops. There is no journey, no passage, no experience of duration. This seems paradoxical because we observe light taking time to cross space. But that time is measured from our perspective, moving slower than light. For the light itself, there is no journey at all. It exists in a timeless state, simultaneously everywhere along its path. This helps explain why light always travels at the same speed. It has no sense of time in which to experience any change in speed. Energy and mass are interchangeable as shown by EMC superscript 2. Perhaps the most famous equation in all of physics is EMC superscript 2. This simple formula reveals a profound truth. Energy and mass are two forms of the same entity. Mass can be converted into energy, and energy can be converted into mass. The C superscript 2 term, the speed of light squared, is an enormous number, meaning even a tiny amount of mass contains an immense amount of energy. This equivalence is not just theoretical. It underlies nuclear reactions, both in weapons and in power plants. When atomic nuclei split or fuse, a small amount of mass is converted into energy, releasing tremendous power. The sun itself shines because of this process, converting mass into radiant energy through nuclear fusion. Every second, the sun converts about 4 million tons of mass into pure energy. This energy streams outward as light, warming our planet and making life possible. EMC superscript 2 is not merely an equation. It is a window into the deep unity of the universe. The sun loses mass every second by radiating light. The sun does not simply emit light. In doing so, it loses mass. Every photon that leaves the sun carries away a tiny amount of energy. Because energy and mass are equivalent, this means the Sun is gradually becoming lighter. The mass loss is enormous by human standards, about 4 million tons per second. Yet the Sun is so massive, containing about 10 kilograms, that this loss is barely noticeable on human timescales. Over billions of years, however, the effect accumulates. The Sun has lost about 0.1% of its original mass since forming 4.6 billion years ago. This gradual loss is part of the natural aging of stars. Eventually, billions of years from now, the Sun will exhaust its nuclear fuel, expand into a red giant, and shed much of its outer layers into space. The conversion of mass into energy is not just a theoretical curiosity. It is the reason stars shine, the reason we have light and warmth, and the reason life exists on Earth. Particle accelerators confirm relativity by observing mass increase. One of the most direct ways scientists test relativity is by accelerating particles to extremely high speeds in machines known as particle accelerators. As particles such as protons or electrons are pushed closer and closer to light speed, their behavior confirms Einstein's predictions. Instead of accelerating linearly with added energy, the particle's effective mass increases. They become harder to accelerate, requiring more and more energy for smaller and smaller increases in speed. This effect, called relativistic mass increase, does not mean particles gain physical substance. Rather, their inertia grows. They resist acceleration more strongly as they approach light speed. Experiments at facilities like CERN, home of the Large Hadron Collider, routinely observe these effects. Particles moving at 99.999% the speed of light behave exactly as relativity predicts. Their increased inertia, time dilation, and energy all match the equations Einstein wrote more than a century ago. Every particle collision is a confirmation of relativity in action. Space and time themselves were created at the Big Bang. If time is part of spacetime and spacetime can be warped and shaped, then what existed before the Big Bang? According to modern cosmology, the answer is that there was no before. Time itself began with the Big Bang about 13.8 billion years ago. The universe emerged from an unimaginably hot, dense state. In that moment, spacetime itself came into existence. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The question has no answer because there was no time before time began. The Big Bang was not an explosion into pre-existing space. It was the creation of space and time together. Everything that exists, all matter, all energy, all distance, and all duration originated in that singular event. The universe has been expanding and evolving ever since, carrying us forward on the river of time that began at that initial moment. The universe is about 13.8 billion years old. By studying light from distant galaxies, the cosmic microwave background radiation, and the large-scale structure of the cosmos, astronomers have determined the age of the universe with remarkable precision. It is approximately 13.8 billion years old. This figure represents the time elapsed since the Big Bang measured in a frame of reference where the universe expands uniformly. Of course, due to relativity, observers moving at different speeds or in different gravitational fields would measure slightly different amounts of time. But for observers moving with the average expansion of the universe, cosmic time is about 13.8 billion years. This means the oldest stars, the first galaxies, and the earliest structures in the universe cannot be older than this. It also means everything we see, from the most distant quasar to the atoms in our own bodies, shares a common origin in that ancient beginning. Before the Big Bang, there was no space, no time, no matter. The Big Bang marks a boundary in time beyond which our current understanding of physics cannot extend. The laws of general relativity, which describe spacetime so well, break down under the extreme conditions of the universe's first moments. At the instant of creation, densities and temperatures were infinite, and the equations yield meaningless results. This does not mean the Big Bang did not happen. It means that our current theories are incomplete. Physicists continue developing theories of quantum gravity that might explain what occurs at such extremes, perhaps revealing that the Big Bang emerged from an earlier state or that time itself behaves differently near the beginning. For now, the Big Bang remains the earliest moment we can describe, the point where spacetime as we know it began. Before that there was no before, no space to occupy, no time to measure, only the mathematical singularity where our understanding reaches its limit. The universe is expanding, carrying galaxies apart. One of the most important discoveries of the 20th century is that the universe is not static. It is expanding. Galaxies are moving away from each other, not because they are flying through space, but because space itself is stretching. Imagine dots on the surface of an inflating balloon. As the balloon expands, the dots move apart, not because they are sliding across the surface, but because the surface itself is growing. This expansion was first observed by Edwin Hubble in 1929, who noticed that distant galaxies are redshifted. Their light stretched to longer wavelengths by the expansion of space. The farther away a galaxy is, the faster it appears to recede. This relationship, known as Hubble's law, shows that the universe is uniformly expanding in all directions. The expansion does not have a center. Every point in space sees other points moving away. This cosmic expansion is carrying galaxies apart, gradually thinning the universe and making it colder and emptier as eons pass. This expansion means the universe had a beginning. The fact that the universe is expanding has a profound implication. If we run the expansion backward in time, the universe must have been smaller in the past. Galaxies were closer together. The space between them was compressed, and matter and energy were more densely packed. If you continue rewinding, you eventually reach a moment when all the matter and energy in the universe were compressed into an infinitely small, infinitely dense point. This is the Big Bang. The moment when the universe began, the expansion we observe today is the continuation of that initial burst. The universe started small and has been growing ever since. Observations of the cosmic microwave background, the afterglow of the Big Bang, provide a snapshot of the universe when it was only about 380,000 years old. At that time it was filled with hot plasma which cooled and became transparent as it expanded. The light from that moment has been traveling through space ever since, redshifted by expansion into microwaves. It is the oldest light in the universe. A direct view into the cosmic past. Some parts of the universe are moving away faster than light. Here is a surprising fact. While nothing can move through space faster than light, space itself has no such speed limit. In the far reaches of the observable universe, galaxies are being carried away from us by the expansion of space at speeds faster than light. This does not violate relativity because the galaxies are not moving through space faster than light. Space itself is expanding, and the cumulative effect over vast distances makes distant galaxies recede faster than light relative to us. This means there are regions of the universe we can never observe. No matter how long we wait or how powerful our telescopes become, the light from these regions will never reach us because the space between us is expanding too quickly. There is a cosmic horizon beyond which the universe is forever hidden. The observable universe is only a portion of the total universe. Beyond our horizon, there may be countless galaxies, stars, and perhaps civilizations, but their light will never reach our eyes. The expansion of space has drawn a veil across the cosmos that no technology can pierce. Dark energy is accelerating the expansion of the universe. For decades, astronomers assumed that the expansion of the universe should be slowing down. Gravity, after all, pulls matter together, and even a uniformly expanding universe should feel gravity's braking effect. But in 1998, two teams of astronomers made a shocking discovery. By observing distant supernova, they found that the expansion of the universe is not slowing down, it is speeding up. This acceleration implies the existence of a mysterious form of energy now called dark energy that fills all of space and pushes the universe to expand faster over time. Dark energy makes up about 68% of the total energy content of the universe. We do not know what it is. It does not emit light. It does not interact with matter in any way we can detect directly. But its gravitational effect is undeniable. It is the dominant force shaping the large-scale structure and fate of the cosmos. As dark energy continues to drive acceleration, galaxies will move apart faster and faster, and the universe will become increasingly cold, dark, and empty over trillions of years. In the far future, galaxies will become isolated islands. If dark energy continues to accelerate the expansion, the universe's future is both vast and lonely. Billions of years from now, galaxies outside our local group will have moved so far away that their light will no longer reach us. The Milky Way and its neighbors, Andromeda, and a few smaller galaxies will eventually merge into a single large galaxy. From within this merged galaxy, future astronomers would look out and see nothing but darkness. The cosmic microwave background will have redshifted into invisibility. Distant galaxies will have vanished beyond the horizon. The stars within the merged galaxy will age and die, and no new stars will form once the available gas is exhausted. Over trillions of years, the universe will become a cold, dark expanse with isolated islands of dead stars separated by unimaginable distances. This is not a comforting vision, but it is the likely fate. If current observations hold true, the universe will not end in a dramatic collapse, but in a slow, quiet fade into darkness. Time dilation affects satellite communications and space missions. As humanity ventures into space, we must account for relativity in practical ways. Communication satellites orbiting Earth experience both gravitational time dilation and time dilation due to their orbital speeds. Engineers must factor these effects into the satellite's programming to ensure signals remain synchronized with ground stations. Without correction, timing errors would accumulate, leading to communication failures and navigation errors. Future missions to other planets will encounter even more dramatic effects. A base on the surface of a massive planet or near a strong gravitational source would experience time differently than mission control on Earth. Astronauts on such missions would need to account for these differences when coordinating activities. Relativity is not just an abstract theory for physicists. It is a practical consideration for space exploration, essential for maintaining accurate clocks, navigation, and communication across the solar system. On Mercury, time passes slightly faster than on Earth. Even within our solar system, different worlds experience time differently due to gravitational time dilation. Mercury, the closest planet to the Sun, sits deep in the Sun's gravitational well compared to Earth, which is farther from the Sun. Time on Mercury runs slightly slower due to the stronger gravitational field. However, this effect is partially offset by other factors, such as Mercury's lower mass and different orbital characteristics. While the differences are tiny, sensitive instruments can detect them. If we ever establish settlements on different planets, inhabitants would age at slightly different rates depending on the gravitational environment they live in. Over many generations, these tiny differences could accumulate. A civilization spread across multiple worlds would need to account for the fact that time itself flows at different rates depending on where you live. Relativity shapes not just our understanding of the cosmos, but the future of humanity as a space faring species. Neutron stars spin hundreds of times per second, warping spacetime. Among the strangest objects in the cosmos are neutron stars, the collapsed cores of massive stars left behind after supernova explosions. These objects pack more mass than the Sun into a sphere only about 20 kilometers across. Their density is so extreme that a teaspoon of neutron star material would weigh as much as a mountain. The gravity on their surface is billions of times stronger than Earth's, and spacetime is severely warped in their vicinity. Many neutron stars spin at astonishing rates, some rotating hundreds of times per second. This rotation drags spacetime itself around the star, a phenomenon called frame dragging. Near the surface, spacetime swirls like water circling a drain. An observer orbiting a neutron star would be pulled along by this rotation, unable to remain still relative to a distant observer. Time dilation near a neutron star is also extreme. A clock on its surface would run noticeably slower than a clock far away. These bizarre objects are natural laboratories for testing the most extreme predictions of general relativity. Frame dragging has been detected near Earth's rotation. Frame dragging is not limited to neutron stars. Any rotating mass drags spacetime along with it. Though the effect is usually tiny, Earth itself causes frame dragging, warping spacetime very slightly due to its rotation. In 2011, NASA's Gravity Probe B experiment confirmed this effect by measuring the tiny changes in the orientation of ultra-sensitive gyroscopes orbiting Earth. The gyroscopes experienced a drift caused by Earth's rotation, pulling spacetime around with it. The effect was minuscule, less than 1,000th of a degree per year, but it was measurable. This confirmed yet another prediction of general relativity. Spacetime is not a passive stage, but an active participant in the physics of the universe. Every spinning object, from planets to galaxies, twists the fabric of reality around it. Though the effects are usually imperceptible, they are always there, shaping the paths of objects and the flow of time. Gravity waves ripple through spacetime. When massive objects collide. When two black holes or neutron stars spiral toward each other and merge, they release enormous amounts of energy in the form of gravitational waves. These are ripples in spacetime itself. Distortions that propagate outward at the speed of light. Just as a stone thrown into a pond creates ripples on the water's surface, violent cosmic events create ripples in the fabric of spacetime. Gravitational waves were predicted by Einstein in 1916, but they were not directly detected until 2015, nearly a century later. The Laser Interferometer Gravitational Wave Observatory LIGO detected the faint signal of two black holes merging over a billion light-years away. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. But by the time the waves reached Earth, they had weakened to an almost imperceptible shiver. The detection opened a new way of observing the universe, not through light but through the vibrations of spacetime itself. LIGO detected gravitational waves from colliding black holes when LIGO made its first detection on 14 September 2015. It marked the beginning of a new era in astronomy. The observatory consists of two facilities, one in Louisiana and one in Washington, each with long arms stretching several kilometers. Laser beams travel back and forth along these arms, measuring their lengths with extraordinary precision. When a gravitational wave passes, it stretches spacetime in one direction and compresses it in another, causing the arm lengths to change by an amount smaller than the width of a proton. This infinite decimal distortion was enough for LIGO's detectors. The signal matched exactly what Einstein's equations predicted for two black holes, each about 30 times the mass of the Sun, spiraling together and merging. The event lasted only a fraction of a second, but it confirmed that black holes exist, that they can merge, and that gravitational waves travel at the speed of light. Since that first detection, LIGO and its partner observatories have detected dozens of black hole and neutron star mergers, each one revealing details about the nature of spacetime and gravity. These waves carry information about events we could never see with light. Gravitational waves offer a completely new way to observe the universe. Light cannot escape from inside a black hole. So the final moments of a black hole merger are invisible to telescopes, but gravitational waves emerge from the collision itself, carrying information about the black hole's masses, spins, and the dynamics of the merger. Even events hidden from light, like the interior of a collapsing star, or the final moments before two black holes become one, can be studied through their gravitational signals. This is like gaining a new sense. For centuries, humans explored the cosmos through light. Now, we can listen to the vibrations of spacetime. Gravitational wave astronomy is still in its infancy, but it has already revealed surprises such as black holes more massive than expected and neutron star collisions that produce gold and platinum. As detectors improve, we will hear more of these cosmic events, each one a message from the violent heart of the universe written in the language of rippling spacetime. Gravitational waves stretch and squeeze space as they pass. When a gravitational wave passes through Earth, it does something remarkable. It stretches spacetime in one direction while compressing it in another. These distortions are incredibly tiny. The strongest waves detected so far changed the length of LIGO's 4 km arms by less than 1,000th the width of a proton. To put this in perspective, it is like measuring the distance to the nearest star to within the width of a human hair. Despite their weakness, gravitational waves are real physical distortions of spacetime. As one passes through you, you would be imperceptibly stretched and compressed. Though the effect is far too small to feel or cause any harm, objects separated by large distances oscillate slightly relative to each other. Spacetime itself is breathing, flexing under the influence of distant cataclysms. These waves traveled across the universe for billions of years, carrying the signature of their violent origins, finally washing over us like whispers from the deep past. Detecting gravitational waves required technology of astonishing precision. The engineering required to detect gravitational waves borders on the miraculous. LIGO's mirrors must be isolated from all sources of vibration. Earthquakes, traffic, ocean waves, even the thermal motion of atoms can drown out the signal. The mirrors are suspended by complex systems to dampen vibrations. And the laser systems measure distances to precisions that defy imagination. The achievement represents decades of work by thousands of scientists and engineers. Early attempts in the 1960s and 70s failed to detect anything. But researchers persisted, refining their techniques and building ever more sensitive instruments. When LIGO finally succeeded, it vindicated not only Einstein's theory, but the dedication of everyone who believed that listening to spacetime's vibrations was possible. Today, gravitational wave observatories are operating around the world, and plans are underway for space-based detectors that could hear waves from the earliest moments after the Big Bang. Time travel to the past may be impossible due to causality violations. The prospect of traveling backward in time has fascinated people for generations. Could we visit the past, meet our ancestors, or witness historical events firsthand? According to our current understanding of physics, backward time travel faces severe, perhaps insurmountable obstacles. The main problem is causality. If you could travel backward through time, you might create paradoxes, such as preventing your own birth or changing events in ways that conflict with the present. These so-called grandfather paradoxes suggest that backward time travel may be fundamentally impossible. Some physicists have explored exotic solutions within general relativity, including closed time lake curves, paths through spacetime that loop back onto themselves. These solutions exist mathematically, but they require conditions that may not be physically achievable, such as negative energy or infinitely long rotating cylinders. Most scientists believe that some yet unknown law of physics blocks backward time travel, preserving causality. Until evidence suggests otherwise, the past remains beyond our reach, accessible only through memory and records. Closed time lake curves exist in theory, but may not be possible. Within the equations of general relativity, there are solutions where spacetime curves so extremely that you could travel forward in time and return to the exact spacetime location where you began. These paths are known as closed time lake curves. One famous example is the Gödel solution discovered by mathematician Kurt Gödel in 1949, which describes a rotating universe where travel to the past is possible. However, these solutions require conditions that do not appear to exist in our universe. Gödel's rotating universe does not match observations. Our universe is expanding, not rotating in the required way. Other proposed time travel solutions require exotic matter with negative energy density, which may not be possible to create or maintain. While general relativity allows closed time lake curves mathematically, nature seems to prevent them in reality. Most physicists suspect that a complete theory of quantum gravity will eliminate them entirely, ensuring that time travel to the past remains fictional. Wormholes could theoretically link distant points in spacetime. Another exotic prediction of general relativity is the wormhole, a tunnel through spacetime connecting to far-separated locations. Imagine folding a sheet of paper and piercing a hole through both layers. A wormhole is like that hole, a shortcut through the fabric of spacetime. If such structures existed and could be stabilized, they would allow travel between distant regions of the universe without crossing the space in between. In principle, a wormhole could also connect different times. Entering one end might cause you to exit the other at a different moment, effectively allowing time travel. However, wormholes face major theoretical challenges. Keeping a wormhole open would require exotic matter with negative energy, which may not exist. Even if one could be created, it might be violently unstable, collapsing the instant anything attempted to pass through. In addition, wormholes that allow time travel could produce the same causality paradoxes as other time machines. While wormholes are compelling in science fiction, their real-world existence remains speculative. Hawking proposed a chronology protection conjecture. Physicist Stephen Hawking was troubled by the idea of time travel to the past and the paradoxes it implied. In 1992, he proposed the chronology protection conjecture, suggesting that the laws of physics prevent the formation of closed time-like curves except possibly on microscopic scales. In other words, nature forbids time machines. Hawking's conjecture remains unproven, but it aligns with observation. We have never seen evidence of visitors from the future, nor do we observe space-time structures that would permit backward time travel. If such travel were possible and common, we might expect encounters with future travelers. Their absence suggests that something prevents backward time travel. Whether this is a fundamental law or a practical impossibility remains unresolved. For now, time's arrow points in a single direction, and the past stays close only through memory and imagination. The arrow of time points from past to future. But why? We experience time as flowing in one direction. We remember the past, not the future. Eggs break but do not reassemble. Heat flows from hot to cold, never the reverse. This one-way flow is known as the arrow of time. But why does time have an arrow? The fundamental laws of physics, from Newton's laws to general relativity, are mostly time-symmetric. They function the same forward or backward in time. The explanation lies in thermodynamics and entropy. Entropy measures disorder, and the second law of thermodynamics states that entropy tends to increase in isolated systems. The universe began in a highly ordered state, the Big Bang, and has grown more disordered ever since. This increase in entropy gives time its direction. We perceive increasing entropy as the future. The arrow of time is not a fundamental law but an emergent property of a universe that began in a low entropy state. As the universe ages, disorder grows, and this process defines time as we experience it. Entropy always increases, giving time a direction. Imagine a drop of ink falling into a glass of water. At first, the ink is concentrated, a low entropy state. Over time, it spreads and mixes until the water is uniformly colored, a higher entropy state. This process is irreversible. You never see the ink spontaneously gather back into a drop. This is the second law of thermodynamics in action. On a cosmic scale, the universe behaves the same way. Energy spreads out, temperature differences even out, and organized structures slowly break down. Stars burn fuel, converting concentrated nuclear energy into diffuse radiation. Living organisms consume energy to maintain order, but in doing so, they increase entropy around them. Every irreversible process, from breaking an egg to aging, reflects the universe's progression toward higher entropy. This relentless increase defines time's arrow, pointing from an ordered past toward a disordered future. The universe began in an extremely low entropy state. If entropy always increases, then the universe must have started with very low entropy. The Big Bang was not only the beginning of space and time, but also the beginning of order. In those early moments, energy was distributed almost uniformly, though tiny fluctuations existed. Gravity amplified these fluctuations, causing matter to clump into stars, galaxies, and clusters. This appears paradoxical because gravity creates clumping, which looks like increasing order. But gravitationally bound systems actually have higher entropy when clumped than when spread out. A star, for example, represents a higher entropy state than the diffuse gas from which it formed. The universe's initial low entropy allowed complex structures to arise. Yet the overall trend always moves toward disorder. Why the universe began in such a low entropy state is one of cosmology's deepest mysteries. It may relate to the nature of the Big Bang itself or to deeper principles we do not yet understand. Without rising entropy, we could not distinguish past from future. Our experience of time depends on entropy. Memory works because the past leaves traces, low-entropy patterns we can interpret. A photograph is a low-entropy record of a moment. Your brain stores memories through physical patterns formed in the past. If entropy did not increase, there would be no difference between past and future. Processes would be reversible, and memory and causality would lose meaning. In a universe where entropy stayed constant or decreased, time itself would lose significance. There would be no clear past or future, only timeless equilibrium. But we inhabit a universe that began in low entropy and evolves toward higher entropy. This evolution allows us to experience time as a flow, to remember the past and anticipate the future. The arrow of time is deeply tied to the structure and history of the cosmos. It explains why we can observe the universe's past in distant galaxies and why the future remains unseen until it arrives. Black holes possess the highest entropy of any objects in the universe. One of the most surprising insights at the intersection of general relativity and thermodynamics is that black holes have entropy. In the 1970s, physicist Jacob Bekenstein proposed that a black hole's entropy is proportional to the area of its event horizon. The larger the black hole, the more entropy it contains. In fact, black holes hold the maximum possible entropy for their size. No other object can store more entropy within the same volume. This discovery linked thermodynamics, quantum mechanics, and gravity in unexpected ways. It suggested that information falling into a black hole is not destroyed but somehow encoded on its surface. This idea inspired the holographic principle, which proposes that all the information in a three-dimensional region can be represented on its two-dimensional boundary. Black holes are not merely gravitational extremes. They are thermodynamic objects with temperature and entropy obeying the same laws as everyday systems. Their existence bridges the gap between the very large world of relativity and the very small world of quantum mechanics. Black holes emit Hawking radiation and slowly evaporate. In 1974, Stephen Hawking made a remarkable prediction. Black holes are not completely black. Due to quantum effects near the event horizon, they emit radiation, now called Hawking radiation. This causes black holes to lose mass over time and slowly evaporate. For a black hole with the mass of the Sun, this process takes far longer than the current age of the universe. Smaller black holes evaporate more quickly. A tiny black hole with the mass of a mountain would vanish in a fraction of a second, releasing a burst of energy. As a black hole shrinks, its temperature rises. In its final moments, it would emit an intense flash before disappearing entirely. This process has not been observed because stellar mass black holes evaporate extremely slowly. Still, Hawking radiation is widely accepted because it naturally arises from combining quantum mechanics with general relativity. It also raises deep questions. When a black hole evaporates, what happens to the information about everything that fell in? This black hole information paradox remains one of the most profound problems in theoretical physics, suggesting that our understanding of space, time, and information is incomplete. The information paradox challenges modern physics. It arises from a conflict between general relativity and quantum mechanics. In quantum mechanics, information cannot be destroyed. Knowing a system's complete quantum state allows its past and future to be reconstructed. But if information falls into a black hole that later evaporates, where does that information go? Hawking radiation appears random, carrying no information about what entered the black hole. This implies information loss, violating a core principle of quantum theory. Physicists have debated this paradox for decades. Some propose that information is hidden in subtle correlations within the radiation. Others suggest it is stored on the event horizon or preserved in a remnant after evaporation. Some argue that spacetime itself has a deeper structure that protects information. Resolving the information paradox likely requires a theory of quantum gravity that unifies relativity and quantum mechanics. Until then, the paradox stands as evidence that our current theories, powerful as they are, remain incomplete. There are still mysteries at the boundary between the very large and the very small. Time may be quantized into discrete units at the smallest scales. In everyday life, time appears continuous, flowing smoothly like a river. But some theories suggest that at extremely small scales, time may be quantized, existing in discrete units rather than a continuous stream, much like matter is made of atoms and energy comes in quantum packets. Time itself may have a smallest unit. This idea arises naturally in attempts to combine quantum mechanics with general relativity at distances near the Planck length, about 10 to the minus 35 meters, and times near the Planck. Time, about 10 to the minus 44 seconds. Spacetime may have a fundamentally grainy structure. Below these scales, the smooth geometry of spacetime described by relativity may break down, replaced by something discrete and quantum. We have no experimental evidence for quantized time yet, but several approaches to quantum gravity, such as loop quantum gravity, predict it. If time is quantized, it would profoundly alter our understanding of the universe at its deepest level and might help resolve paradoxes involving black holes and the Big Bang. At the Planck scale, spacetime itself may become uncertain. The Planck scale marks the limit of our current theories. Below the Planck length and Planck time, quantum fluctuations become so intense that spacetime becomes fuzzy and indeterminate. In quantum mechanics, the Heisenberg uncertainty principle limits how precisely certain quantities can be known. At the Planck scale, this uncertainty extends to spacetime itself. Distances and durations lose definite meaning, and the smooth fabric of spacetime may dissolve into a turbulent foam of quantum fluctuations. In this realm, concepts like before and after or here and there may cease to apply. The Planck scale lies far beyond any experiment we can imagine, many orders of magnitude smaller than a proton. Yet it marks the frontier where our understanding must evolve. Physicists hope that a theory of quantum gravity will explain what happens at these scales, revealing whether spacetime is fundamental or emerges from something deeper. String theory proposes extra dimensions beyond the familiar three of space. One of the most ambitious attempts to unify all forces, including gravity, is string theory. In this framework, the fundamental constituents of reality are not particles, but tiny vibrating strings of energy. Different vibrations correspond to different particles, such as electrons, photons, and gravitons. Each is a string vibrating in a unique way. String theory requires more than the familiar 3 dimensions of space and 1 of time. Most versions require 10 dimensions, with 6 curled up so tightly that we cannot detect them. These extra dimensions could significantly influence physics, shaping particle properties and forces. In some models, our entire universe is a 3-dimensional surface, a brain floating in a higher dimensional space. Time itself might have additional dimensions in these theories, though this remains speculative. String theory has not yet been experimentally confirmed, but it provides a mathematically consistent framework for describing gravity at the quantum level. If it is accurate, the universe is far stranger and more intricate than our everyday experience implies, with hidden dimensions woven into the fabric of reality itself. Loop quantum gravity quantizes spacetime into discrete loops. An alternative to string theory is loop quantum gravity, which takes a different path toward unifying quantum mechanics and general relativity. Instead of replacing particles with strings, loop quantum gravity concentrates on spacetime itself. It proposes that spacetime is not continuous but composed of discrete loops, a kind of quantum foam at the smallest scales. In this view, space is woven from loops of gravitational field lines, and time emerges from the dynamics of these loops. At large scales, the loops blend together and spacetime appears smooth, just as fabric looks smooth even though it is woven from individual threads. But zoom in far enough, and the discrete structure becomes visible. Loop quantum gravity predicts that there is a smallest possible volume and a shortest possible time. This theory has had some success describing the interiors of black holes and the very early universe, suggesting that the Big Bang might have been a bounce from a previous contracting phase rather than a true beginning. Like string theory, loop quantum gravity remains speculative, but it offers a different vision of how spacetime behaves at the quantum level, one where space and time themselves are emergent phenomena arising from deeper quantum structures. The measurement of time depends on the observer's frame of reference. One of the most profound lessons of relativity is that there is no single correct way to measure time. Time depends on your frame of reference, your state of motion, and your position in a gravitational field. Two observers moving at different speeds or at different locations in a gravitational field will measure different intervals of time for the same events. This does not mean time is subjective or that measurements are incorrect. Each observer's measurements are valid within their own frame of reference. Time is relative, but the laws of physics are the same for everyone. This consistency allows us to make predictions and understand the universe. Despite the fact that time flows differently for different observers, the relativity of time is not a flaw in our understanding. It is a fundamental feature of reality. Proper time is the time measured by a clock moving with you. In relativity, there is a special term for the time measured by a clock that travels with you. It is called proper time. No matter what path you take through space-time, no matter how fast you move or which gravitational fields you pass through, your wristwatch measures your proper time. It is the time you experience directly, the time that governs your aging and your perception of duration. Different observers moving along different paths through space-time will measure different amounts of proper time between the same two events. The traveling twin in the twin paradox experiences less proper time than the stay-at-home twin. A photon experiences zero proper time along its entire journey. Proper time is the ultimate personal clock, the measure of duration in your own frame of reference. It is invariant for you even though it may differ from the proper time measured by someone else on a different path. Coordinate time is the time measured by a distant observer. While proper time is what you measure on your own clock, coordinate time is the time assigned to events by a distant observer using a particular coordinate system. For example, if you are on Earth and want to describe events happening on a distant spacecraft, you assign them times in Earth's reference frame. This is coordinate time. Coordinate time is useful for describing events from a consistent external perspective, but it is not the time experienced by the objects involved. A spacecraft speeding away at relativistic speeds experiences far less proper time than the coordinate time measured on Earth. Neither measurement is wrong. They are simply different perspectives on the same events. Relativity teaches us to be careful about which time we refer to and to recognize that time is not a single universal quantity but depends on how we choose to measure it. Simultaneity is relative. Events simultaneous for one observer may not be for another. Imagine two events occurring in space, a supernova exploding in one galaxy and a star being born in another. Are these events simultaneous? The answer depends on who you ask. For an observer moving at high speed relative to both galaxies, the two events might occur at the same time. For another observer moving differently, one event might happen before the other. This relativity of simultaneity is a direct consequence of the finite speed of light and the structure of spacetime. There is no universal now that stretches across the cosmos. Different observers divide spacetime into slices of time in different ways. Events that appear simultaneous in one frame of reference occur at different times in another. This does not create contradictions because causally connected events that can influence each other, always maintain their order for all observers. It is only events separated by distances too great for light to travel between them in time that can have ambiguous ordering. The light cone divides spacetime into past, future, and elsewhere to understand causality in spacetime. Physicists use the concept of the light cone. Imagine a point in spacetime representing an event, say you reading this sentence right now. From this point, you can draw paths representing light rays traveling into the future and into the past. These paths form a cone shape in spacetime. The future light cone contains all events that you can influence. The past light cone contains all events that could have influenced you. Everything outside the light cone is called elsewhere. These are events too far away in space and too close in time for you to affect or be affected by them. Your light cone defines the boundary of your causal influence. No signal, no force, no information can travel faster than light. So everything outside your light cone is causally disconnected from you at this moment. The light cone structure is fundamental to how relativity preserves causality and prevents paradoxes. Causality is preserved. Effects cannot precede causes. One of the most important features of relativity is that causality is always preserved. Even though different observers may disagree on the order of some events, they can never disagree on the order of causally connected events. If event A causes event B, all observers will agree that A happened before B. This is because causal signals like light or any other interaction cannot travel faster than light. The structure of spacetime ensures that causes always precede their effects. The speed of light acts as a cosmic speed limit that prevents information from traveling backward in time. This is why faster than light travel, if it were possible, would lead to paradoxes. It would allow effects to precede their causes in some reference frames. By limiting all signals to the speed of light or slower, relativity protects causality and ensures that the universe remains logically consistent. The speed of light is the speed of causality. It is often said that the speed of light is the ultimate speed limit. But a deeper way to think about it is that the speed of light is the speed of causality. It is the speed at which effects propagate through the universe. Any massless particle, not just photons, travels at this speed. Gravitational waves also travel at the speed of light. This speed is woven into the structure of spacetime itself. Even if light did not exist, the speed of causality would still be the same. It is a property of spacetime, not of light specifically. Light simply happens to be the most familiar phenomenon that travels at this speed. When physicists talk about the speed of light, they are really talking about the maximum speed at which information or influence can travel. It is the cosmic speed limit that ensures causality, preserves the order of events, and gives spacetime its structure. Einstein's equations describe how mass and energy curve spacetime. At the heart of general relativity are Einstein's field equations, a set of 10 interrelated equations that describe how matter and energy tell spacetime how to curve and how curved spacetime tells matter how to move. These equations are elegant in their compactness, but incredibly rich in their implications. They predict everything from the orbit of Mercury to the expansion of the universe to the existence of black holes. Solving Einstein's equations is notoriously difficult. Only a few exact solutions are known, such as the Schwarzschild solution for a non-rotating black hole and the Kerr solution for a rotating one. Most real-world situations require numerical simulations on powerful computers. Yet despite their complexity, the equations have been tested countless times and have never failed. They are among the most successful theories in the history of science, describing gravity with precision across scales from millimeters to the entire observable universe. These equations predicted black holes before they were observed. When Carl Schwarzschild found the first exact solution to Einstein's equations in 1916, just months after the theory was published, the solution described something astonishing. A mass compressed into a sufficiently small region would create a boundary from which not even light could escape. This was the first mathematical description of a black hole, though the term would not be coined for decades. At the time, many physicists, including Einstein himself, doubted such objects could exist in nature. They seemed too extreme, too strange. But over the following decades, astronomers found indirect evidence for black holes. And in 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow. Einstein's equations predicted this reality long before technology could confirm it. The equations have proven more insightful than even their creator expected, revealing aspects of the universe that stretch human imagination. Relativity has been tested countless times and never proven wrong. For more than a century, general relativity has been subjected to rigorous experimental tests. Every test has confirmed its predictions. The bending of starlight by the sun observed during solar eclipses. The precession of Mercury's orbit, which could not be explained by Newtonian gravity. Gravitational time dilation measured with atomic clocks. The existence of black holes confirmed through gravitational waves and direct imaging. The expansion of the universe observed through the redshift of distant galaxies. All of these and many more observations agree with relativity. There are still frontiers where relativity meets quantum mechanics and our understanding is incomplete. But within its domain, describing gravity and space-time from millimeters to the cosmos, general relativity has never been contradicted by experiment. It stands as one of the most thoroughly validated theories in all of science. Its success is a testament to the power of human reason and the deep mathematical beauty underlying the physical universe. Time travel to the future is possible and has been demonstrated. While traveling to the past remains speculative and likely impossible, traveling to the future is not only possible but has been demonstrated. Every time you move, you travel into the future of those who remain stationary. Astronauts aboard the International Space Station have traveled measurably into Earth's future, aging slightly less than people on the ground due to time dilation. If we could build spacecraft capable of traveling at speeds close to light, we could send astronauts decades or centuries into the future during a journey that for them lasts only months or years. This is not science fiction. It is a direct consequence of relativity. The engineering challenges are immense, requiring propulsion systems far beyond current technology. But the physics is clear. Time travel to the future is real, and it happens every time anything moves. You are traveling into the future right now at 1 second per second. There is a sense in which time travel is not special at all. You are moving into the future at this very moment at the rate of 1 second per second. This may seem like a trivial observation, but it highlights an important truth. Time is something we move through just as we move through space. We cannot stop or reverse our motion through time, but we are always moving forward. The difference relativity introduces is that the rate of this motion can vary. Move fast or enter a strong gravitational field, and you can travel into the future faster relative to others. But even sitting still, you are journeying into the future. Every heartbeat, every breath, every thought is a step forward through time. The future is not a distant place. It is where you are heading moment by moment, carried by the inexorable flow of time that began with the universe itself. The universe might be infinite, making the concept of cosmic time complex. When we talk about the age of the universe, we refer to cosmic time, the time measured by observers moving with the overall expansion of the universe. But if the universe is spatially infinite, which is possible, then the concept of a single cosmic time becomes more complex. Different regions of an infinite universe separated by vast distances might be at different stages of evolution with no single moment that can be called now for the entire cosmos. The observable universe, the part we can see, is finite with a well-defined age of about 13.8 billion years. But beyond the observable horizon, the universe may extend infinitely in all directions. In such a universe, time becomes even more profoundly relative. There may be no universal present moment extending across all of space. Instead, time is a local property defined by the history and evolution of each region. The universe may be a vast patchwork of different nows, each valid in its own domain. In some models, time itself might end or change its nature. Some speculative models suggest that time might not continue forever in its current form. If dark energy continues to accelerate the expansion, the universe might experience a big rip where space expands so rapidly that even atoms are torn apart. In such a scenario, the structure of spacetime itself might be destroyed and time as we know it could end. Other models propose a big crunch where the expansion reverses and the universe collapses back into a singularity. Time might not extend beyond that final moment. Still, other theories suggest that time could undergo phase transitions, changing its nature just as water changes from liquid to ice. Near the Big Bang, time might have behaved differently than it does now. These ideas remain speculative, but they remind us that time, despite its familiarity, is still deeply mysterious. Its nature, origin, and ultimate fate are questions that push the boundaries of science and philosophy. Cosmological models explore whether time is finite or infinite. Does time extend endlessly into the past and future, or are there boundaries? Current cosmology places a boundary in the past, the Big Bang, where time began. But what about the future? If the universe expands forever, driven by dark energy, time may continue indefinitely. The universe would grow cold and empty, but time itself would stretch on without end. Alternatively, if some unknown process eventually reverses the expansion, time might end in a big crunch. Some cyclic models propose that the universe undergoes repeated cycles of expansion and contraction, with time extending infinitely through an endless series of cosmic epochs. Each cycle may feature a Big Bang followed by a big crunch, with time flowing from one to the next. These models are speculative, but they show how cosmology wrestles with the deepest questions about the nature and extent of time. The anthropic principle asks why the universe appears suited for life. One curious feature of our universe is that the laws of physics and the values of fundamental constants seem finely tuned to allow life to arise. If gravity were slightly stronger or weaker, if the electron's mass were different, if the expansion rate of the universe were altered just a bit, stars might not form, atoms might not exist, or the universe might have collapsed or spread apart too quickly for galaxies to develop. This apparent fine-tuning raises an important question. Why is the universe so well suited for life? The anthropic principle offers one way of thinking about it. We observe the universe to be life-permitting because if it were not, we would not be here to observe it. In a multiverse scenario where countless universes exist with different properties, only those rare universes with the right conditions can support observers. This does not explain why our universe has the properties it does, but it provides a framework for understanding the observation. Alternatively, there may be deeper reasons rooted in physics we do not yet grasp that determine the constants of nature. Multiverse theories propose countless universes with different physical laws. If the multiverse exists, our universe is just one among an unimaginably vast collection of universes, each with its own physical laws, constants, and perhaps even different numbers of dimensions. In some universes, time might flow differently. In others, it might not exist at all. Most of these universes would be sterile, unable to support complexity or life. We find ourselves in one of the rare universes where conditions permit observers because by necessity we can only exist in such a place. Multiverse theories are controversial because they are difficult or impossible to test. If other universes are forever beyond our reach, can we ever confirm their existence? Yet the idea arises naturally from certain theories, such as eternal inflation in cosmology and the many worlds interpretation of quantum mechanics. The multiverse remains one of the most speculative and intriguing ideas in modern physics. The search for a theory of everything seeks to unify all forces. Physicists dream of a theory of everything, a single framework that unites all the fundamental forces of nature and explains all physical phenomena. Such a theory would merge general relativity, which describes gravity and spacetime, with quantum mechanics, which describes the other forces and the behavior of particles. It would address questions about the nature of time, the origin of the universe, and the fate of black holes. Candidates for a theory of everything include string theory, loop quantum gravity, and other approaches. None have been confirmed experimentally. It is also possible that a complete theory will require ideas we have not yet imagined. The search for this theory is not only about unifying equations. It is about understanding the deepest nature of reality. What is spacetime made of? Why does time flow? How did the universe begin? These questions have fascinated humanity for millennia, and physics is slowly moving closer to answers. Time remains one of the deepest mysteries still unsolved. Despite all we have learned, time remains enigmatic. We understand how it flows at different rates, how it is interwoven with space, how it is influenced by gravity and motion, but we do not fully understand what time is. Why does it exist? Why does it have a direction? Is it fundamental or does it emerge from something deeper? Does time exist independently of the universe, or is it inseparable from the fabric of spacetime? These questions lie at the boundary between physics and philosophy. Time shapes every aspect of our existence, yet it resists complete understanding. As we probe deeper into reality, time continues to surprise us, revealing layers of complexity and beauty. It reminds us that the universe is not fully known, that mysteries remain, and that the quest to understand time is an endless journey. Looking at the stars is looking into the past. When you gaze into the night sky, you are seeing the universe not as it is now, but as it once was. Light from the nearest stars took years to reach you. Light from distant galaxies took millions or even billions of years. You are looking backward through time, seeing objects as they were when their light began its journey. The farther you look, the deeper into the past you peer. Astronomers use this property to study cosmic history. By observing distant galaxies, they see what the universe looked like billions of years ago when it was younger and very different. Telescopes are time machines, not because they take us to the past, but because they reveal the past. Every photon that reaches your eye is a messenger from history, carrying information across time as well as space. To look at the stars is to witness the unfolding story of the universe written in light. We are made of atoms forged in ancient stars. The atoms that make up your body, the carbon in your cells, the oxygen you breathe, the iron in your blood were not present at the Big Bang. They were created in the cores of stars that lived and died billions of years ago. When those stars exhausted their fuel, they exploded as supernovae, scattering enriched material into space. That material later came together to form new stars, planets, and eventually you. You are literally made of stardust. The universe has a history, and that history is recorded in the atoms you carry. The heavy elements in your body were forged in stellar furnaces shaped by nuclear reactions long before the sun or earth existed. In a very real sense, you are a child of the cosmos, a temporary assembly of ancient atoms that have traveled through time and space to come together as you. Every moment connects you to the entire history of the universe. There is an unbroken chain of cause and effect linking you to the Big Bang. Every breath you take involves oxygen atoms created in stars. The sunlight that warms your face began as nuclear fusion deep within the sun. The ground beneath your feet is made of rock that condensed from the primordial solar nebula billions of years ago. You are not separate from the universe. You are part of it, woven into its fabric across time. Your existence depends on countless events stretching back to the beginning of time. The formation of the first atoms, the birth of the first stars, the creation of heavy elements, the formation of the solar system, the development of Earth, the emergence of life, and the long evolutionary journey leading to humanity. Each moment of your life is the culmination of this vast history. You are the universe experiencing itself, a temporary pattern in the cosmic dance, connected to all that came before and all that will come after. Time is both personal and universal. Time is personal. It is the heartbeat of your life, the rhythm of your days, the measure of your aging. But time is also universal, woven into the fabric of reality, shaping the evolution of stars, galaxies, and the cosmos itself. Every being experiences time in its own way, yet all are part of the same space-time continuum. The time you experience is unique to your path through the universe, yet connected to the time experienced by every other observer. This duality is part of what makes time so fascinating and elusive. It is intimately familiar yet deeply mysterious. It is subjective yet governed by objective laws. It is personal yet universal. Time bridges the gap between the individual and the cosmos, between the fleeting and the eternal. It reminds us that we are both unique and part of something far greater than ourselves. Understanding time changes how we see ourselves. When you understand that time is relative, that it bends and stretches, that it began with the universe and may one day end, your perspective shifts. You realize that the moment you experience now is not the same as someone else's now. You see that aging is not absolute but depends on motion and position. You understand that looking outward is looking backward, that the universe reveals itself across time as well as space. This knowledge can be humbling. It shows how small we are within the vastness of space-time and how brief our lives are compared to cosmic timescales. But it can also inspire. It reveals that we are part of a grand story, participants in the unfolding universe. Understanding time deepens our appreciation for the preciousness of each moment and the profound interconnectedness of all things. Time connects us to everyone who has ever lived. The same time that carries you forward carried every human before you. Ancient civilizations, artists, explorers, and scientists all moved through time just as you do now. They looked up at the same stars, though those stars were slightly younger then. They experienced the flow of time, the passage of days and seasons, the steady march toward the future. Though separated by centuries or millennia, all humans share the experience of time. We are all traveling together through the same space-time continuum, each on our own path, yet part of the same journey. Time links generations, connecting past to present to future. The knowledge accumulated by those before shapes your understanding, and your actions ripple forward to influence those who come after. Time is the thread that binds humanity across the ages. The present moment is all we truly have. Despite discussions of past and future, of time dilation and cosmic clocks, one simple truth remains. The present moment is all we ever experience. The past exists only in memory and records. The future exists only in anticipation and imagination. All you truly have is now. This moment, this breath, this heartbeat, even as relativity teaches that now itself is relative. Your experience of now is absolute for you. This makes each moment precious. Time flows forward, and once a moment passes, it is gone forever, joining the ever-growing past. You cannot return to it or relive it. All you can do is be fully present here, experiencing this moment as it unfolds. The study of time, for all its mathematical elegance and cosmic scope, ultimately leads back to this simple truth. Now is where life happens. Now is where you exist, and now is all you have. Time is a gift flowing endlessly forward. In the grand scheme of the cosmos, time is the stage on which everything unfolds. Stars are born and die. Galaxies collide and merge. Particles interact and decay, all within the flow of time. For living beings, time is even more. It is the medium of experience, the framework of memory, the canvas of hope. It allows change, growth, and the unfolding of stories. Time is also a gift. It gives you the opportunity to learn, to love, to wonder, and to create. Without time, there would be no journey, no development, no meaning. Time carries you from the past into the future, offering each moment as a new beginning. Even as you understand its relativity, its flexibility, and its deep connection to the universe's structure, you can appreciate time for what it gives you, the chance to be here now, alive and aware. We are all time travelers moving steadily into the future. In the most literal sense, you are a time traveler. You move through time at 1 second per second, always heading forward. You cannot stop or slow your own clock. From another perspective, if you moved fast enough or entered a strong gravitational field, others would see your clock slow. From your own view, time always flows at the same rate, carrying you onward. This journey through time is shared by everyone and everything in the universe. Photons race at light speed, experiencing no time at all. Muons created in the upper atmosphere live brief lives, yet reach the ground due to time dilation. Astronauts orbit Earth, aging slightly less. And you sit here reading, breathing, thinking, moving through time at your steady pace. Each of us is a time traveler, and the journey unfolds moment by moment. The flow of time is the heartbeat of existence. Time gives rhythm to the universe. It is the pulse driving stars through their life cycles, the beat carrying planets along their orbits, the tempo governing particle decay and cosmic expansion. Without time, there would be no motion, no change, no causality. The universe would be frozen and static. Time makes the universe dynamic, alive, and evolving. For conscious beings, time is even more intimate. It is the heartbeat of experience. Thoughts unfold in time. Emotions shift and evolve. Memories anchor us to the past. Anticipation draws us toward the future. Awareness exists in the present. Time is not merely the backdrop of life. It is the essence of existence, the medium through which we live and perceive. To exist is to move through time. Time will outlast us. But we are part of its story. Long after humans are gone, time will continue. Stars will burn, galaxies will drift, black holes will evaporate on timescales beyond imagination. The universe will age, and time will carry it forward whether or not observers remain. Time does not depend on us. It is a feature of space-time itself, as fundamental as the dimensions of space. Yet for a brief flicker in cosmic history, we are here. Conscious observers aware of time's passage, able to measure it, study it, and wonder about it. We are part of time's story, a fleeting pattern in the flow of existence. Our lives are short compared to the age of the universe, but in this moment we are alive, aware, and connected to the vast history of time stretching from the Big Bang to the infinite future. Imagine time as an endless river carrying everything forward. Picture time as a vast river flowing from past to future. Everything that exists is carried by its current. Stars and planets, light and energy, thoughts and memories all drift along the stream. The river never stops or reverses. It moves only one way, from the ordered past toward the disordered future, following the arrow of entropy. You are a small vessel on this river, floating with everything else. Sometimes the waters are calm, sometimes rapid. Sometimes you move quickly, sometimes slowly, depending on speed and gravity around you. But you are always moving, always carried forward. The river of time is vast beyond comprehension, and you are part of its flow, one among countless travelers journeying from the beginning toward an unknown future. Time can feel slow or fast, but it always moves at the same pace for you. Have you noticed how time seems to pass differently depending on what you are doing? When you are engaged and joyful, hours can vanish in what feels like minutes. When you are bored or in pain, minutes can stretch into what feels like hours. This is a psychological effect, a quirk in how your brain processes experience. Objectively, from your own frame of reference, time always moves at exactly the same rate, 1 second per second. Relativity tells us that this rate can differ when compared to others. If you travel fast enough or enter a strong gravitational field, observers elsewhere will see your clock slowing, yet you will notice no change at all. Time will feel normal to you, always flowing at a steady pace. This is one of the elegant symmetries of relativity. No matter where you are or how you move, your personal experience of time remains constant and unchanged. Only when you compare your clock with someone else's do the differences reveal themselves. The mystery of time invites us to reflect. For all that science has uncovered, time remains one of the deepest mysteries of the universe. What is it truly? Why does it flow in a single direction? How is it connected to space? Does it have a beginning and an end, or does it extend infinitely? Is time fundamental, or does it arise from something more basic? These questions still lack complete answers. They sit at the frontier of human understanding, urging us to explore, to question, and to wonder. This sense of wonder is what makes the study of time so fulfilling. It links science to the most profound questions of existence. It reminds us that the universe is rich with mysteries waiting to be discovered, and it invites each of us to think, to imagine, and to marvel at the strange and beautiful reality we inhabit. Time is not merely a concept to analyze. It is an invitation to wonder. Relativity reveals that the universe is stranger than we once believed. Before Einstein, time seemed simple, the steady ticking of a universal clock, identical for everyone everywhere. Space was viewed as a fixed stage on which events played out. But relativity shattered this simplicity. It showed that time and space are interwoven, that time can slow down or speed up, that simultaneity is relative, and that the past and future depend on perspective. The universe revealed by relativity is far stranger and far more wondrous than we imagine. It is a place where black holes twist space-time into extremes, where gravitational waves ripple through the cosmos, where twins can age at different rates, and where looking outward means looking backward in time. This strangeness is not a flaw. It is reality's true nature, made more beautiful by how unexpected it is, so far beyond intuition, so deeply mathematical and precise. The universe does not care whether its workings feel strange to us. Relativity functions whether we understand it or not. Clocks tick at different rates, light always travels at the same speed, and space-time curves around mass. These are facts of nature, as dependable as mathematics itself. The universe follows its own logic, indifferent to human intuition. This can feel humbling, yet also empowering. It shows that the universe is understandable. Through observation, experiment, and reason, humans have uncovered truths about time and space that would have seemed magical to our ancestors. We have built technologies like GPS that rely on relativity. We have detected gravitational waves and captured images of black holes. The universe may be strange, but it is knowable, and we have only begun to explore its depths. Every tick of the clock is a step into an unknown future. With each passing second, you move farther from the past and deeper into what lies ahead. The future is uncertain, a vast landscape of possibilities stretching forward. You cannot see it or know what it holds. It is shaped by choices, by chance, and by the unfolding of physical laws across countless interactions. Each moment opens new possibilities while closing others. This journey into the unknown is what makes life dynamic and unpredictable. You cannot return to the past, and you cannot fully know the future. All you truly have is the present, this moment, and the choices you make within it. Time carries you forward, but how you use each moment is up to you. The future is not fixed. It is created moment by moment through the actions of everything that exists, including you. Time teaches us to value the fleeting beauty of now. Because time flows forward and moments pass irreversibly, each one is unique and brief. You will never experience this exact moment again. The people you love, the sights you see, the thoughts you think all exist only within this narrow window of now. Once gone, they become part of the growing archive of the past, accessible only through memory. This impermanence gives life its poignancy. Knowing time is limited makes each moment precious. It teaches us to appreciate what we have, to be present, to savor the experience of being alive. The study of time, despite all its equations and abstractions, ultimately brings us back to this simple wisdom. Pay attention. Be here now. Time is moving, and this moment is a gift that will not return. To understand time is to understand the fabric of reality. Time is not just a measurement or a dimension. It is part of the universe's fundamental structure. To grasp time is to see how reality operates, to understand the relationship between matter, energy, and space-time. It is to follow the universe's evolution from the Big Bang to the present and into the distant future. It is to comprehend causality, gravity, and the flow of entropy. This understanding connects you to humanity's deepest knowledge, placing you in a lineage of thinkers from ancient philosophers to modern physicists who continue to probe time's mysteries. To wonder about time is to join the oldest and grandest quest, the search to understand existence itself. The night sky is a window into spacetime. When you look up on a clear night, you are not only seeing space, you are seeing spacetime, the four-dimensional fabric weaving together distance and duration. Every star is a point in both space and time. Light from the nearest star left years ago, while light from distant galaxies began its journey billions of years in the past. You are looking across light years, units that measure both distance and time. In a real sense, the sky is a map of history, revealing the universe as it once was, layer upon layer of time written in light. Gazing at the stars lets you witness the interplay of space and time, to see how light crosses vast gulfs of space-time to reach your eyes. The night sky is not only beautiful, it is profound, a visible expression of relativity and a reminder that space and time cannot be separated. Space exploration pushes our understanding of time even further. As humans venture beyond Earth, we encounter relativity in practical ways. Missions to other planets, to the moons of Jupiter, and perhaps one day to other stars will require accounting for time dilation, for differences in gravitational fields, and for communication delays as signals travel at light speed. Astronauts moving at high speeds will experience time differently than those who remain behind. Future colonies on distant worlds will measure time at rates subtly different from Earth's. As we become a spacefaring species, we will learn to navigate spacetime, not just space. Exploring the cosmos is also an exploration of time, driving us to understand its nature more deeply. Time is the medium of memory and imagination. Without time, memory could not exist. Memory preserves past moments, encoding what was into the structure of the brain, allowing learning and identity to persist across time. Imagination also depends on time, projecting forward or backward to envision what might have been or what could be. Memory and imagination are two sides of the same coin, one reaching into the past and the other into the future. Both are enabled by the flow of time and the arrow of entropy. In a universe without time's direction, without a distinction between past and future, memory and imagination would lose meaning. Time gives structure to consciousness, making you more than a fleeting instant. It allows you to be a being with history and hope. The speed of light links the smallest and largest scales. As the cosmic speed limit, it connects the quantum world to the vastness of the cosmos. On the smallest scales, particles interact through photons moving at light speed. On the largest scales, light from distant galaxies travels billions of years to reach us. The same constant appears in equations describing both subatomic interactions and cosmic expansion. This universality makes the speed of light fundamental. It is not merely a property of light, but of space-time itself, defining relationships between space and time, energy and mass, cause and effect. From the smallest particle to the largest galaxy, a single thread connects all scales. Time allows the universe to evolve and change. Without time, the universe would be static, with no motion, no history, no development. Stars would not form or die, galaxies would not emerge, and life could not evolve. Time makes the universe dynamic, allowing the initial conditions of the Big Bang to unfold into the rich and complex cosmos we inhabit. The universe's evolution over nearly 14 billion years, from hot dense plasma to stars, galaxies, planets, and life, is a story told through time. Each stage builds upon the last, guided by physical laws and entropy's arrow. Time is the axis along which this grand narrative unfolds, turning possibility into reality, transforming potential into the present moment. Every moment belongs to an unbroken continuum stretching back to the Big Bang. A continuous path through space-time connects now to every moment before it. Cause and effect, particle interactions, and gravity link the present to the past in an unbroken chain. Nothing exists in isolation. Everything is connected through time. You are part of this continuum. The atoms in your body were forged in stars, which formed from gas enriched by earlier stars, which arose from the primordial material of the Big Bang. Each step is linked by time, causality, and cosmic evolution. To exist is to be a link in this chain, a temporary pattern in the flow of space-time stretching from the beginning into the future. The journey through time is shared by all. No matter who you are or where you are moving through time. From the smallest microbe to the largest galaxy, everything advances through time at its own pace, shaped by motion and position in space-time. We are all time travelers, part of the same cosmic story. This shared journey connects us, reminding us that we belong to something larger, participants in the universe's unfolding. Though our individual paths may differ, we are all carried by the same river of time toward an unknown future. In this lies a deep unity that transcends distance and difference. Time is the canvas upon which existence is painted. If space-time is the fabric of reality, time is the dimension that allows patterns to form and evolve. Stroke by stroke, moment by moment, every event, interaction, and thought leaves its mark on the ever-changing picture of existence. The painting is unfinished. The universe continues to evolve, to create, and to surprise. New stars ignite, new planets form, and new life may arise in distant corners of the cosmos. The canvas of time stretches onward, finite or infinite, we do not know, but always present, always offering the medium for existence to express itself. And so, traveler through time, our journey into the mysteries of relativity draws to a close. From learning that time flows at different rates depending on motion and gravity, to understanding that space and time are woven together, to discovering that the universe had a beginning and continues to expand, we have explored the strange and beautiful nature of time. We have seen how relativity reshapes reality, explains GPS satellites and distant starlight, predicts black holes and gravitational waves. We have faced paradoxes and puzzles, from the twin paradox to the arrow of time and the nature of now. Through it all we glimpse the truth that time is not what it seems. As you rest, your breath slowing and thoughts drifting, Imagine yourself floating on the river of time. Feel it carry you gently from one moment to the next. Picture the vast expanse of space-time around you, woven from countless moments and observers, each moving through their own time. See the stars above, their light traveling across ages to reach you. Feel your connection to the universe, to ancient stardust, to entropy's flow, to the constants shaping reality. You are part of this. You are a traveler through space-time, moving forward in the cosmic dance. Time flows through and around you, carrying the universe onward. And as you drift into sleep, into dreams, and quiet stillness, know that time continues its journey. The universe keeps evolving. The stars keep burning. The river keeps flowing. And you, for this brief and precious moment, are here, aware, alive, experiencing the gift of time. If you are still awake, you may rest now, letting time carry you gently into sleep. And if your eyes are already closing, if your thoughts are fading into softness, let yourself drift. Float on the current of time, always forward, into peaceful rest. Close your eyes, breathe deeply, and let time cradle you as it cradles all things in its endless, gentle flow. Good night,